The universe never ceases to surprise us, but sometimes it also leaves us with more questions than answers. Take the case of GJ 1132b, for instance, a distant exoplanet that has been a subject of fascination and debate among astronomers. The latest findings from the James Webb Space Telescope, JWST, suggest something groundbreaking. GJ 1132b likely doesn't have an atmosphere. And this discovery could reshape how we think about planets orbiting M-dwarf stars. But here's where it gets controversial. What does this mean for the broader search for habitable worlds? Let's dive in. In science, conflicting data isn't a sign of failure. Rather, it's a natural part of the process. It simply means researchers need more evidence to draw solid conclusions. One recent example of such a puzzle came from observations of GJ 1132b, a rocky exoplanet located about 41 light-years away. Depending on which dataset you looked at, GJ 1132b either had an atmosphere or didn't. Sorting through these contradictions became a challenge, but now, thanks to extended observations with JWST, scientists are coming closer to resolving the mystery. Their conclusion? GJ 1132b is most likely devoid of any significant atmosphere. This finding has profound implications for exoplanet research as a whole. So why all the fuss about GJ 1132b? Well, this planet is intriguing because it shares some similarities with Earth while being starkly different in other ways. For starters, GJ 1132b is rocky, with a radius and mass only slightly larger than our home planet. However, it orbits its M-dwarf star at a scorching distance of just 0.0153 astronomical units (AU), completing one orbit every 1.6 days. Given its extreme proximity to its host star, it might seem astonishing that anyone would even consider the possibility of an atmosphere existing there. Yet, some theoretical models suggest that planets near active M-dwarf stars can retain atmospheres under certain conditions. This leads us to a key concept in exoplanetary science, the cosmic shoreline. Think of it as a boundary line determined by factors like stellar irradiation and planetary size, beyond which planets struggle to hold on to their atmospheres. M-dwarf stars, known for their intense radiation and frequent flares, pose a significant threat to the atmospheric stability of nearby planets. With GJ 1132b sitting so close to its volatile star, the odds were already stacked against it retaining an atmosphere. But what makes this study particularly interesting is the journey to reach this conclusion. Earlier studies using JWST data presented conflicting results. In one transit observation, the data hinted at a water-rich atmosphere enveloping the planet. In another, it appeared completely barren. To resolve this discrepancy, researchers conducted 2 additional transits, bringing the total number of datasets to 4. When analyzed collectively, the overwhelming consensus emerged. GJ 1132b lacks an atmosphere. There's still a sliver of ambiguity, though. The data allows for the faint possibility of a very thin, low-pressure steam atmosphere, hovering around 1 millibar. However, given the planet's proximity to its star and earlier indications of water scarcity, most experts dismiss this scenario as highly unlikely. Notably, if you exclude the initial dataset, which suggested the presence of a water-based atmosphere, the remaining 3 datasets unanimously agree that no atmosphere exists. So, what went wrong with that first set of data? Upon closer inspection, the researchers identified a potential culprit: variations in the star itself. During the first transit, the M-dwarf exhibited more cool spots on its surface compared to subsequent observations. These cool spots, essentially regions of lower temperature, skewed the measurements and created the illusion of an atmosphere where none existed. This revelation highlights the importance of cross-checking multiple datasets, especially when dealing with highly variable stars. The authors propose adopting a leave-one-out approach, essentially analyzing subsets of data independently to mitigate similar issues in future studies. Another fascinating aspect of this research lies in the methods used to gather the data. The team employed two distinct viewing modes of JWST's NIR spec instrument: G395H, high resolution, and G395M, medium resolution. While the high-resolution mode offers sharper details, it comes with a minor drawback: a gap in its spectral coverage between 3.75 and 3.82 microns. Despite this, the noise levels between the two modes turned out to be comparable, making both viable options depending on the situation. The researchers recommend using the medium-resolution mode for single-transit studies due to its efficiency, while reserving the high-resolution mode for cases involving multiple transits. At its core, this paper settles a long-standing debate about GJ1132b's atmospheric status, or lack thereof. Beyond that, it provides valuable lessons for improving the reliability of exoplanet studies moving forward. By addressing the confusion surrounding this specific planet, the authors offer tools and strategies to prevent similar ambiguities in future research. Perhaps most importantly, this work adds another piece to the cosmic puzzle regarding whether planets orbiting M-dwarf stars can maintain atmospheres. And the evidence seems to tilt heavily toward no. What do you think? Do you believe M-dwarf planets stand a chance at retaining atmospheres despite the odds? Or does this study confirm your suspicions that they're doomed to remain barren wastelands? Share your thoughts in the comments below.